So in the last video, we learned about the product rule. In this video, I want to review that a tiny bit, but then talk about the quotient rule. As the name kind of implies, the product rule helps you when you're taking the derivative of something times something. So for example, the derivative of x squared times the natural log of x. Whereas the quotient rule comes into play when, well, you're taking the derivative of a quotient. So something like the derivative of the natural log of x divided by x squared. But before I tell you the quotient rule, which you can kind of sort of see down here, I want to make the point that for this specific derivative, we could use the product rule. A common theme in calculus is often it'll be beneficial to rewrite expressions so that they fit one of our rules. And in this specific instance, if you were trying to figure out the derivative of the natural log of x divided by x squared, and you had the ability to rewrite this as the natural log of x times x to the negative 2 power, then you wouldn't need the quotient rule at all, right? It's the derivative of something times something. If you can change division into multiplication by taking advantage of what you might already know about negative exponents, then just use the product rule right here. The derivative of something times something is the derivative of the first thing, the natural log of x, times the second thing, x to the negative 2 power, plus the derivative of the second thing, x to the negative 2 power, times the natural log of x. And since I know the derivative of the natural log of x, that's just 1 over x, I'll get 1 over x times x to the negative 2 power. And then since I know the derivative of x to the negative 2 power, let's see, I'd use the power rule. I'd bring the negative 2 down in front and then subtract 1 from that exponent to get negative 2x to the negative 3. I just have to multiply that by the natural log of x. The derivative of this quotient is this expression right here. We could rewrite this expression if we felt the need, but really this just falls into the category of simplification. X to the negative 2 power is the same as 1 over x squared. And when I'm adding a negative, I'm really just subtracting. And 2x to the negative 3 power is the same as 2 divided by x cubed. So negative 2x to the negative 3 power can be rewritten this way. And since I'm multiplying that by natural log of x, I can think about this as the natural log of x over 1 and make this negative 2 natural log of x divided by x cubed. Why would you want to do that? Well, 1 over x times 1 over x squared simplifies pretty nicely. It's 1 over x cubed. So really I have 1 over x cubed minus 2 times the natural log of x over x cubed. And as long as I've come this far, I might as well recognize that I have a common denominator here for these two fractions. So I can subtract the fractions and get 1 minus 2 times the natural log of x divided by x cubed. Really, we stopped doing calculus once we got to this line right here, right? You could call this your answer if you wanted, but it's a good idea to be able to simplify and end up with an answer like this, both because this answer is prettier than this answer up here, but also because the ability to rewrite things mathematically will be so important when we start to put all these different rules together and you're given an expression that doesn't look like anything that fits any of the rules you have. So it's not just an exercise for aesthetics to get my answer to look nice like this. There really is a method to all this madness. Anyways, the point is that if you were asked to find this derivative, you could use the product rule. But there's other ways you could do it as well. And you're like, yeah, I'm not interested in another way. You tell me one way, I'll remember that one way, I'm good. And I'm like, yeah, but what if it was this problem instead? What if instead of natural log of x divided by x squared, it was x squared divided by the natural log of x? Very similar to what we see up here. But the problem is down here, we can't rewrite it as a product taking advantage of negative exponents because we don't have x raised up to some power down here in the denominator. Yeah, you could make it x squared times, and then in parentheses, natural log of x to the negative 1 power. But if you did that, you wouldn't be able to figure out the derivative because you don't know the derivative of the natural log of x raised up to the negative 1 power yet. So in this case, you're kind of stuck. You could rewrite it if you want, but you won't be able to rewrite it in a way that'll allow you to use the product rule. Damn, that's too bad. What can I do? Well, there's this thing called the quotient rule. And it looks really ugly, right, when we write it in this standard notation. But what it's saying isn't quite as bad as it looks. It says if you're trying to take the derivative of something divided by something else, what you do is you take the derivative of the top thing and multiply it by the bottom thing. Note that we're only taking the derivative of the top here, not the g of x. Kind of like with the product rule. It's the derivative of one of them times the other one. In the product rule, you add something to that. In the quotient rule, you instead subtract. What do you subtract? Well, it'd be really nice if it was the derivative of the other thing times the first thing, and it's exactly that. If you can almost see the product rule up here in the numerator, that'll make it a lot easier for you to remember these different rules. The numerator of the quotient rule is identical to the product rule, except we have a negative sign in between the terms instead of a positive sign in between the terms. Unfortunately, the differences don't stop there. For the quotient rule, we also have a denominator. We got to divide by g of x squared. Not the derivative of g of x squared, not the second derivative of g of x or something, just g of x, whatever's down on the bottom, squared. So when you're using the quotient rule, there's really only two calculus parts. Take the derivative of the top here, that's one of them, and you take the derivative of the bottom over here. There's no other derivatives in this formula. Rarely do people memorize the quotient rule in this form because you can write it shorthand in this form, which is so much easier to look at. F over g prime is f prime g, the derivative of f times g, minus g prime f, that's kind of important, there has to be an f there, divided by g squared. Okay, I think I got the formula for the quotient rule. Can I actually see it in action? Absolutely. Why don't we redo this problem right here with the quotient rule and make sure we get the same answer? The derivative of the natural log of x divided by x squared using the quotient rule is the derivative of the top, the derivative of the natural log of x, times x squared. From that, we want to subtract the derivative of x squared times the natural log of x. And then don't forget, we have to divide that whole thing by the bottom x squared squared. You'll get to the point where you don't have to write out this step at all and you can jump straight to this next line. But for this first time through, I thought it might be instructive for you to see all the different parts and see where they go in the formulas. The derivative of the natural log of x is 1 over x. I want to take that derivative and multiply it by x squared. From that, I want to subtract the derivative of x squared, which using the power rule is just 2x, times the natural log of x. And then I want to divide that entire thing by x squared squared. Maybe remember that exponents raised up to exponents means you multiply these two exponents to get x to the fourth. Another way to realize that this is x to the fourth is thinking about when I'm squaring something, I'm multiplying it by itself. So this is x squared times x squared, and I can add up those two 2's to get this x to the fourth, whichever way makes more sense to you. My answer looks different here and here, but I think they're equivalent. And if we simplify this a little bit, we'll be able to see that. 1 over x times x squared, one of these x's and this x cancels, so I'm left with just an x. And then over here, I got 2x natural log of x divided by x to the fourth power. You might recognize that each of your terms up in the numerator here has an x in them. I can factor out an x and I'd be left with 1 minus 2 natural log of x. This x and this x go right here. And then I divide that by x to the fourth power. Why would you want to do such things? Because now that I have this multiplication, I can cancel this x with one of these x's, and I'm left with 1 minus 2 times the natural log of x divided by x to the third power, which is the exact same thing that I had written up here. What about the derivative of x squared over the natural log of x? If you're a little bit uncomfortable with these rules, you can write it out like this. But trust me, you'll quickly get to the stage where you want to just look at this and be like, the derivative of the top is 2x. I'm going to multiply that by the bottom. From that, I'm going to subtract the derivative of the bottom, which is 1 over x, and I'm going to multiply that by the top, x squared. And then don't forget to divide the entire thing by the bottom, natural log of x squared. The derivative of x squared over natural log of x is this mess of an expression, which is probably not a bad idea to simplify a little bit. 2x natural log of x minus x divided by the natural log of x. Yeah, you could factor out an x from the top, but there's nothing to cancel it with in the bottom, so I'd probably just call that good. To make sure this is sinking in, I want to show you a couple of examples, and even a case where you could have used the quotient rule, but you don't need to, then we'll call this video good. The derivative of the natural log of x divided by x squared minus 5x. Can you do this maybe all in one step? Let's see, I take the derivative of the top, which again is 1 over x, and I'd multiply that by the bottom, which is x squared minus 5x. Be really careful here. Make sure that you put parentheses here. Otherwise, your 1 over x will just hit the x squared. I want it to hit this entire thing. I want the derivative of the top to get multiplied by the entire bottom here. From that, I want to subtract the derivative of the bottom, which is 2x minus 5. Hopefully we're at the point in the class where you can look at this and tell that the derivative of this is 2x minus 5. If not, maybe do that off to the side. Figure out the derivative of x squared minus 5x in a couple of different lines, and eventually you'll get 2x minus 5 as your answer. Where was I over here? Oh, right, I took the derivative of the bottom, but I still have to multiply that by the top, the natural log of x. And then I'm done? No. Don't forget that you always have to divide by the denominator over here squared. So x squared minus 5x squared. Can I simplify this thing? Yeah. Should I? I don't know. I mean, I guess if you want to. I would probably at least multiply this through the parentheses to get x minus 5. And then, I don't know, since we're already getting rid of parentheses, I guess you could take the negative natural log of x and distribute that through these parentheses to get negative 2x natural log of x plus 5 natural log of x. I don't know, maybe you don't even do that. Whatever you think is prettier. And then down on the bottom here, if you really wanted to expand this to x squared minus 5x times x squared minus 5x, you could. I don't want to. I'm going to leave it as x squared minus 5x squared, and I kind of wish I hadn't even gone any further than this. Either of these are perfectly acceptable answers in our class. Here's one more example that's a good one for you to start on your own. Think about if you could take the derivative of this. And you might be like, this looks like it's in the wrong spot because it's something times something. Shouldn't this be in the product rule section? How about this as a hint? It's not in the product rule section for a reason, right? Try to use the product rule on this thing and I think you'll get into trouble because you don't know the derivative of e to the negative x power. Damn, that's too bad. But what do you do when your derivative rules kind of fail you on an expression? Well, maybe you can rewrite that expression. E to the negative x power is the same as 1 divided by e to the positive x power, right? That's what negative exponents do. So I could rewrite this question this way, and now all of a sudden, it fits my quotient rule really nicely. The top is something I could take the derivative of. The bottom is something I could take the derivative of. I'm home free. The derivative of x to the fourth is 4x cubed. I want to take that and multiply it by e to the x, the bottom. Then from that, I want to subtract the derivative of e to the x, which just happens to also be e to the x, times the top, which is x to the fourth. And then I want to take that big expression and divide the entire thing by the bottom, e to the x squared. Optional simplification. In this case, this simplifies kind of nicely, so you probably do want to do it. Recognize that you have an e to the x in each of these terms. So you could pull that out in front and you'd be left with 4x cubed minus x to the fourth. Why would you want to do that? Well, because down on the bottom, you got two of these e to the x things multiplied together. So I could take one of these e to the x and this e to the x and cancel those out, and I'd be left with just 4x cubed minus x to the fourth divided by e to the x to the first power. This is an acceptable answer, but this is kind of a prettier answer. And if you can get to the point where you can look at this and kind of tell that it can be simplified, it's a good idea to go ahead and do it. One more example. Here's a derivative that you really could evaluate using the quotient rule, and you'll get the right answer. You don't have to, there's an easier way, but I think it's instructive to see how the quotient rule gives you the same answer that you would have got if you evaluated this another way. So maybe first think about, could you evaluate this without any quotient rule, without using anything new from this video, using the methods of the previous section? The idea there is you'd probably want to rewrite this so that it's the derivative of 6 times x to the negative 2 power. So we're no longer dividing by x to the positive 2 power. And then you can just leave this 2/3 alone. We have the derivative of a sum of two terms. So all we got to do is take the derivative of each one individually. So this derivative of 6x to the negative 2 plus the derivative of 2/3. The derivative of 6x to the negative 2, you bring the 6 out in front. You multiply that by the derivative of x to the negative 2 power, which is negative 2x to the negative 3 power. And when all the dust settles, I think you'll get negative 12x to the negative 3rd power. What about the derivative of 2/3? It's tempting to look at this and use the quotient rule, but you don't need to. I mean, you could if you really wanted to, but because 2/3 is a constant, its derivative is just 0. You don't need to use any rules here at all. You'll get the same answer if you use rules, but don't bother. This is just equal to 0. The derivative of this expression is negative 12x to the negative 3rd power. In other words, negative 12 over x cubed. What if you didn't realize algebraically that 6 over x squared could be rewritten as 6x to the negative 2? Or you were dealing with some other problem that kind of prevented you from doing that? Well, you could still get the same answer. You just have to use the quotient rule. I'm still going to recognize that I have two different terms, and the derivative of the sum of two different terms is just the sum of the two derivatives. So I'll kind of do these two different parts separately. And I'm again going to realize that this is just a constant, so its derivative is just equal to 0. So I'm really focusing over here. Let's use the quotient rule. The quotient rule tells me that I take the derivative of the top. So the derivative of 6 is a constant, that's just 0. And I multiply that by the bottom, which is x squared. And then from that, I want to subtract the derivative of the bottom, which is 2x, times the top, which is this 6. But then I'm not done. I got to make sure that I divide that entire thing by the bottom, x squared, squared. As I already mentioned, this derivative is just 0, so this huge expression is my answer. Is this equal to negative 12x cubed? Well, it better be. Let's see how. 0 times anything is 0. So I have negative 2x times 6 I have negative 12x up on the top. And then on the bottom, I got x squared squared, which as we talked about earlier is x to the fourth power. I can cancel this x with one of these x's, and I get negative 12 over x cubed, the exact same answer that I got over here. I'm not suggesting that you should use the quotient rule on this specific problem. I'm just making the point that you could use the quotient rule and get the same answer. And if you can see how the quotient rule supplies the same answer that our previous section's methods do, maybe that gives a really good understanding of the quotient rule. In case you don't feel super confident about the quotient and the product rules yet, I'm going to make another video that just has a ton of examples in there. It might end up being 2 more videos. We'll see.